Good morning. Welcome back. Section 4 in Chapter 9 is about operations with functions. The operations that we're going to look at 5 of them. 4 of them are really pretty easy. The 5th one is a bit new, and so we're going to spend a lot more time on the 5th one than we are on the other 4. Our learning targets today: I can add, subtract, multiply, and divide functions. Those are the 4 easy ones. And I can write and evaluate composite functions. And you might be wondering, what is a composite function? Well, that's the 5th one. That's the one that's a bit new that we're going to spend time on. Even though it's actually not new. We've been doing this all year. In fact, you did this yesterday, and I'll show you how that's true when we talk about that. So, first one are 4 basic operations. Before we get to doing them, let's get a couple functions to use as examples. Let's use f of x equals x squared plus 3x, and g of x equals 2x plus 6. So our first operation, f plus g of x. If you had to take a guess, what do you think this is telling you to do? If you're saying, oh, I think we should probably add the two together, that would be correct. All this means is f of x plus g of x. It's almost like you can distribute this x through the function notation, which is not entirely true, but that's the way it works. Sometimes notation makes perfect sense, and sometimes it's just really weird. These cases, it just makes perfect sense. So let's figure out what this is. F plus g of x, well, f of x is just x squared plus 3x, g of x is 2x plus 6, so it's x squared plus 3x plus 2x plus 6, combine like terms, 3x plus 2x is 5x, so f plus g of x equals x squared plus 5x plus 6. That's addition. Subtraction, f minus g of x means f of x minus g of x, and the same thing, we're just going to subtract the two. With subtraction, though, we do need to make sure that we distribute this negative through the second function. That would be the biggest mistake in subtraction. And so we'd end up with x squared plus 3x minus 2x minus 6, which is x squared plus x minus 6. The third one, fg of x. If you had to take a guess, f of x times g of x. And so we're going to have f of x times g of x, and then we just need to make sure that we distribute. Yes, you still have to distribute. All the stuff we've learned still holds true. And so we'll have x squared times 2x, which would be 2x cubed, x squared times 6, which is 6x squared, 3x times 2x is another 6x squared, and then 3x times 6 is 18x. And we can combine our like terms. 6x squared plus 6x squared is 12x squared. There, it's multiplied. And then our fourth one, f over g of x, which is f of x divided by g of x. And this one comes with the stipulation, g of x, the denominator, can't equal 0. So we could just plug in our functions, x squared plus 3x over 2x plus 6. We just got done dealing with stuff like this in the last chapter. To simplify, we're going to factor the top. Hey, we can take an x out of each of those to get x times x plus 3. The denominator, we can take a 2 out of each of them to get 2 times x plus 3. So we end up with that. Hey, x plus 3 over x plus 3, that cancels. So we get x over 2. But the denominator can't equal 0, which would be x plus 3 can't equal 0, so x can't equal negative 3. So it equals x over 2, and x can't equal negative 3. So all this stuff is stuff that we've done. The addition, subtraction, and multiplication, actually, we did in the beginning of Chapter 6 on polynomials. This one, yeah, we divided polynomials, but we also just worked on them with rational equations, rational functions in the last chapter. So none of this is new other than the notation. But again, if you just saw the notation, you'd probably figure it out. So the other operation is a composition of functions. So we're going to still use our same two functions here, for the moment at least. Now a composition of functions, the notation looks like this. We have f, then we have this little circle. Looks actually kind of like my laser pointer here. We have a little circle, and then g, then of x. And what this is it's pronounced f of g of x. If we were to write it in the other notation, just like we were doing with the other ones, it would look like this, which is again pronounced f of g of x. And what this means is we're going to take the g of x function and we're going to replace all the x's in the f function with the g of x function. So, looking at an example, f of g of x is x squared plus 3x. That's something squared plus 3 times something. What's going into those somethings? The g of x. 2x minus 6 is going into those open spots. And then from here we're going to simplify. But this is just like if we were doing f of 2. We'd replace all the x's with 2's. We're replacing all the x's with 2x plus 6's. So we do that, and we can simplify. 2x plus 6 squared. Yes, we have to distribute 2x plus 6 times 2x plus 6, which will give us 4x squared. Then we'll have a 12x, another 12x, and a 36. Distribute the 3 to get 6x plus 18. And then we can combine our like terms to get 4x squared plus 30x plus 54. So again, we took the f function, the outside function, and we replaced all the x's with the inside function. X squared, or the x here, and the x here. We can switch the order on this. We can do g of f of x. So we're going to take all the x's in the g function and replace it with the f function. So g is 2 times something plus 6. We're going to fill in that something with f of x. X squared plus 3x. Distribute the 2, and we're done. And so I mentioned that we've been doing this a lot, even yesterday. I already mentioned that when we have f of 2, we replace all the 2's, or all the x's with 2's, but that's kind of the same, not exactly. So how were we doing these yesterday? Well, what were we working on yesterday? We were working on transformations. What happens when we have a horizontal transformation, such as a horizontal translation, g of x equals f of x plus 3? We replace all the x's with x plus 3. That's a composite function. We replace all the x's with 1/2 x. Composite function. Replace all the x's with negative x. It's a composite function because we're replacing all the x's with another function. So we have been doing this throughout the year. And so this is what a composite function is. Here's writing the actual composite functions. Sometimes, though, we're going to be evaluating. And so when we're evaluating composite functions, there are two main types that we end up evaluating. The first is with equations. And so let's bring the two equations back. F of x equals x squared plus 3x and g of x equals 2x plus 6. And we want to evaluate f of g of 2. There's a couple ways of doing this. The first way is we actually find f of g of x. And then we just need to plug in 2. We already found f of g of x. It was right on that the last slide. It was 4x squared plus 30x plus 54. Then we just need to plug in 2 for x. So we get 4 times 2 squared plus 30 times 2 plus 54. 2 squared is 4 times 4 is 16. 30 times 2 is 60 plus 54, and we can add them together to get 130. Now those should still be 2's. So f of g of 2 equals 130. That's one way of doing it. If we've already found this equation, we may as well do it this way. The other way of doing it is very useful if we don't have to find this equation to begin with. And that would be we just take it piece by piece. So let's look at f of g of 2 again. We can do the inside. We're going to look at g of 2. So we're going to plug 2 into g. 2 times 2 is 4 plus 6. So g of 2 is 10. Well, if g of 2 is 10, we really just need to find f of 10. So in the f of x function, we plug in 10. 10 squared plus 3 times 10. It's going to be 100 plus 30. So f of 10 is 130. So f of g of 2 equals 130. A lot easier than having to find this, especially with the distribution. But again, if we already have this, you may as well just plug it in here. And this method, where we do each piece individually, is how we really do the next type. So this is with equations, but we could also be looking at tables. And with tables, we're going to have to kind of do this, except we don't have to do the calculations. So if we have a couple tables, we have an f of x table, and we have a g of x table. So first I want to point out that these are not from these equations. Not at all. In fact, I would not try to find equations for these because I really just kind of randomly made up the numbers for the functions, so that you can't just find an equation and do this. But we have f of x and we have g of x. So we're going to start. Let's find g of f of 2. So we start out with f of 2. We start out with the inside. That's our entry point, f of 2, which is right here, 2. So negative 2 is f of 2. And then we're going to plug negative 2 into the g equation to get 6. So we start out with the inside. We plug that into the other one to get our answer. So g of f of 2 equals 6. We can go the other way. Notice I started g of f here just because that's the way the tables are laid out. What if we had f of g of 4? The entry point is g of 4. So we go to the g table, x equals 4. So we have our entry point. That equals 1. So we plug 1 in to the f table. Well, 1's way over here. And we get 0. So g of f of 4 equals 0. Now, this doesn't come up very often, but people always ask about, well, what if we have g of f of 0? Well, if we have g of f of 0, we start out with f of 0, which is 3, plug it in, and it doesn't fit here. We don't know what g of 3 is. It's just not enough info. Again, I don't think it comes up at all, but it's a question people ask. So if it does come up where you just can't do it because you don't have those values in the table, you don't have enough information to finish it. So those are composite functions where we plug in a function into our other function. We can find them, we can evaluate them using equations and tables. And then we have our 4 basic operations. Again, a lot of today is really easy. The composite functions are really the only part that's new. So we'll be able to make sure we focus on those. But that was it. Enjoy the rest of your evening, and I will see you tomorrow.